Once we have the automorphism group for Z mod n, we consider the automorphism groups for the dihedral groups. Recall, D sub 2n, the dihedral group with 2n elements. Okay, we're going to have n greater than or equal to 3. This is going to be the symmetries of a regular n-sided polygon. So here I have a hexagon. If we arrange our polygon, so it's centered at the origin, I'll put the 1 on the positive real axis. We'll put the other labels in increasing order, going counterclockwise. We could describe D2n completely by the following generators and relations. The generators are going to be R and C. R is the rotation that carries 1 to 2. Okay, that's going to have order n, so we have R to the n of z. C is going to be reflection through the x-axis. If we do that twice, we get back to where we started, so c squared to z. Then we have the relation, if I take R, conjugate by c, note c is order 2, so c equals c inverse, we get R inverse. So this just says, if I flip through the x-axis, rotate, flip again, then I just rotate in the other direction. Now, in practice, the way we use this, okay, we're going to move c to the other side. We note that c is equal to c inverse. So if I have c times r and I want to push r to the other side, it has to pick up an inverse. Now, with that, we could list all the elements in D2n. So we're going to have n rotations, if we count the identity, and n reflections. First punchline, the number of automorphisms in D sub 2n is equal to n times 5n, where phi is the Euler-Totient function. So this is going to be the number of integers. We have m between 1 and n, including 1, and we want m and n relatively prime. Now, let's see this work in an example we already know. So we already know that the automorphism group of S3, symmetric group on 3 letters, is isomorphic to S3. Now note S3 is just another way of saying D6. So Euler-Totient function on 3 is going to be 2, so it's going to be the numbers 1 and 2. Then we're going to have 3 times 5, 3, which is going to give me 6, and that agrees with the number of elements in S3. So that checks out. Let's count the possibilities. We know D sub 2n is generated by R and C. If we have an automorphism pi, where can we send R? Now, we have only one subgroup of order n, the rotation subgroup. So any automorphism has to send that subgroup back to itself. So I need to send R to another generator of that subgroup. Now, our subgroup is isomorphic to Z mod n. So the automorphism group will be Z mod n star. That means R must be sent to some R to the k, where k and n are relatively prime. So that's where the Euler-Totient function comes in. Now, for C, this is of order 2, so we can send that to any other element of order 2, noting that if we have an element of order 2 in the rotation subgroup, that's off limits because that's covered by R. So we could send a reflection to any other reflection. So we have n possibilities. This gives us an upper bound for the number of automorphisms. Turns out that covers all of our automorphisms. So every automorphism pi is going to be of the form R gets sent to R to the k, where k and n are relatively prime, and C is sent to another reflection, C times R to the L, and then L is between 0 and n, including the 0. Now, to see that all of these give automorphisms, let's recall what an automorphism is. Automorphism is going to be a relabeling of the elements of the group in a way that preserves a multiplication. In our case, the multiplication is entirely encoded by the relations. So we want to see when we apply pi to our relations, we get those relations to hold up with our new elements. So let's just check. If I take pi of r, raise it to the nth power, okay, well, we're sending this to r to the k. We could switch the exponents. This goes to the identity, and that's going to give us our first relation when we note if we try this for any smaller n, it's not going to work because k and n are relatively prime. So pi of r has order n. If we take pi of c and square it, okay, so we're sending pi of c to c times r to the L. I'm going to take the middle terms and switch. So remember, the penalty is that the r to the L picks up the inverse. Then we see cancel in pairs. So we get the identity. So these two hold up. Then, for our last one, we're going to conjugate r by c. So what do we have here? CR to the L, r to the k, CR to the L. So we're just going to push this c past the r to the L and r to the k. So they pick up inverses. The two c's cancel. R to the L on the outside takes away the r to the minus L. So we get r to the minus k. And that's pi r inverse. So all of our relations are getting sent to the same relations, just with new elements. Let's compute the normal subgroup of inner automorphisms. So recall, an inner automorphism is an automorphism of the form C sub x for fixed x and g, where C sub x sends g to xgx inverse. So we're going to conjugate each g by x. We have a theorem that states in G is isomorphic to the quotient group G mod the center of G. We've computed the center of D sub 2n before. That turned out to be the identity when n was odd, and when n was even, we had two elements. We had the identity and r to the n over 2. R to the n over 2 was rotation by 180 degrees. Now, our result, n of D sub 2n, is isomorphic to D sub 2n when n is odd, so that's clear from here, and D sub n, or D sub 2 n over 2 when n is even. So for this part, we actually have to show something. Now, what we'll do, we'll consider our quotient group. We'll write out generators and relations in terms of cosets, and then we'll just show that they satisfy the relations for D sub n. So our identity element, okay, we'll denote our elements. Okay, instead of writing cosets, I'll just take a representative element, put a bar on it. So we have E bar is E r to the n over 2. R bar will have r to the 1 plus n over 2. And we note, okay, if we took r, kept raising the powers, we would sweep out all powers of r, okay, not going to the identity until we get to r to the n. For r bar, same idea, but you note, when we get to r to the n over 2, we wind up getting into the identity coset, so we only have half the order here. So r bar to the n over 2 is the identity bar. For the coset with c, okay, we have c r to the n over 2. Well, if we square this, we're going to get the identity bar. And note, this coset is not equal to this coset, so this isn't the identity, which means C bar has order 2. Finally, for the final relation, there's nothing to show here. Okay, note, any relations we have in the original group carry over. The only problem is they may collapse. So if any of your elements were in your normal subgroup, they turn into the identity, we lose information. Now note, your relations can still change meaning. For instance, in this case, if we let n be equal to 4, note that we have r bar squared equal to the identity. So every element in our group has order 2, and we're looking at Z2 cross Z2 now. Note, okay, this we can consider to be a dihedral group, so dihedral group with 4 elements. Let's compute the inner automorphisms explicitly. If we conjugate by rotation, say r to the k, r goes to itself, C goes to R to the K, C R to the minus K. If we push the C to the front, the R to the K picks up a minus sign. Then we get C R to the minus 2K. If we conjugate by reflection, say C R to the K, R goes to C R to the K, R, and then we use the rule for the inverse of a product. So we just switch the order, put the inverse on each term. So we'll have R to the minus K, C inverse. Since C is order 2, C is equal to C inverse. I push this C to the front, and we get R inverse. Likewise, when we compute the effect on C, we get C R to the 2K. So we can characterize all the inner automorphisms as those of the form. We'll send R to R or R inverse. C goes to C times R to an even power. Now, let's check something we already know. If we conjugate by the element in the center, we get the identity map. So this is when n is even. So if I take C of R to the n over 2, R goes to R, C goes to R to the n over 2 times C times R to the minus n over 2. We push the C to the front, and we get C R to the minus n. R to the n is the identity, so we get C back. That means we have the identity map as promised. Now, let's consider the outer automorphism group. So we have out of a group equal to the quotient group, ought of your group, mod by in of the group. First, let's compute the order. So we're going to take number of elements in ought, divide by the number of elements in. When n is odd, number of elements in ought is n phi n. Number of elements in is 2n. So we have phi n over 2. When n is even, number of elements in ought is still n phi n. Number of elements in is n, so we're going to have phi n. Now, what about the outer automorphisms? So what elements are we not getting as inner automorphisms? Well, one thing you'll note, we can work with the exponent on the R. So, to have an automorphism, we need to send R to R to the K, where K and N are relatively prime. And then we can just send C to itself. So we'll call these automorphisms pi sub K. If I take all of these and form a subgroup, then the subgroup is isomorphic to Z mod N star. Now, question is this enough? When N is odd, the answer is yes. We'll get all the outer automorphisms that we need to get out of D2n. In the case N even, this is only going to get us halfway there. To get the other half, I have to consider conjugation by the square root of R. To compute out of D2n, let's first consider the case when N is odd. Then, the inner automorphisms are all the form. R goes to R or R inverse. C can go to any reflection. That follows because, since N is odd, R to the 2L is going to sweep out all the rotations, so we'll get all reflections. Next, we consider the map. Okay, this is going to be the quotient map carrying our automorphism group to out. So all this does, we take an automorphism and we just send it to its coset by in. Now, we want to focus on our subgroup H, which consists of all pi sub k's. So we're going to restrict the quotient map to another map, Q sub H. This map will be a homomorphism, but it might not be onto. So it'll map to a subgroup of out. Because it's a homomorphism, we'd look at the kernel and form a quotient group. So the kernel of Q sub H, this is going to be the set of pi sub k's that are also inner automorphisms. Now, to be a pi sub k, we send R to R to the k. C has to go to itself. The only way we get C to go to itself for an inner automorphism is when we have C sub C. So R goes to R inverse, C goes to C. That means this kernel has two elements. And if I take H mod this kernel, we have phi n over 2 cosets. Now note, the number of elements out of D2n is phi n over 2. This set's going to carry over to a subgroup, so it hits everything. So that says out of D2n is isomorphic to Z mod n star, modded out by the subgroup plus minus 1. Okay, note there, plus 1 corresponds to R going to R, minus 1 corresponds to R going to R inverse. We see by this description that out is abelian when n is odd. To get an idea of what's happening when n is even, let's take a look at the cosets in this case. So if I take pi sub k times n, we're going to have the automorphisms of the form R goes to R plus minus k, C goes to anything. We note coset for pi sub k is the same as the coset for pi sub minus k. Okay, so that's why we're modding out here. Now, what happens in the even case? Well, one thing you'll see, we have to erase any reflection from here. We're only going to be able to send C to C times R to an even power. So if we think in terms of the partition of aught G, if I consider just these, we're going to get all the automorphisms that send C to C times an even power. So we're missing all the ones that have C going to C times R to an odd power. So our construction here would only give phi n over 2 cosets. So how do we get the other half? Well, that's where the square root of R comes in. Let's consider the square root of R the 1/2. If R is the rotation that carries 1 to 2, then R the 1/2 is just going to use half the angle. You'll note R the 1/2 is not a symmetry of the regular polygon. It's not supposed to be. It's supposed to be an automorphism of our group. What's happening here? We're sending axes of reflection to other axes of reflection. Now, what's special about R the 1/2, you'll note, it's going to carry an axis of reflection for a reflection that fixes an opposite pair of vertices to one that fixes an opposite pair of edges. So it's interchanging these two types of reflections. When n is odd, this isn't an issue. Okay, when n is odd, every axis of reflection goes through a vertex and an opposing edge. Now, we should also note when n is even, if we consider the inner automorphisms, it's going to maintain parity. So if I have a reflection fixing an opposite pair of vertices, it goes to another reflection of that type. Similarly for the edges. So by including this CR the 1/2, we're catching the interchange between vertices and edges. Let's compute with the square root of R. First, we'll add conjugation by R the 1/2 to the inner automorphism group. Now, that group's generated by C sub R and C sub C. So the new group will be generated by C sub R the 1/2 and C sub C. We expect another dihedral group. So let's check the relations. Take conjugation by R the 1/2 to powers. If we raise it to the nth power, we're conjugating by R to the n over 2. R to the n over 2 is in the center, so we get the identity. That doesn't happen for any smaller power, so the order of conjugation by R the 1/2 is n. C sub C has order 2, and we have a relation between reflections and rotations. So that means we have a copy of D sub 2n inside of our automorphism group, whether we're odd or even. Now, let's move to the outer automorphism group. So here we're going to consider elements as cosets by Ng. I want to consider the product of pi sub k times conjugation by R the 1/2 in either order. As automorphisms, these are not equal, but you'll note, since n is even, k is relatively prime to n, so that means k is odd. Now, because parity is the same here, these live in the same coset modulo the inner automorphisms. So that means in Alt G, we have these two elements are equal. So pi sub k and conjugation by r to the 1/2 commute in Alt G. Also note, conjugation by r to the 1/2 in Alt G has order 2. If we square it, we get C sub r, which is an inner automorphism. So we're taking our subgroup H, modded out by plus minus 1, adding in an element of order 2. Because this element of order 2 commutes with this other group, we're going to get direct product of Z mod 2 with what we had before. So that describes outer automorphisms of D sub 2n when n is even. Note again, out is abelian in this case. For a concrete example, let's consider D sub 8 the symmetry group of the square. This has 4 times 5, 4, or 8 automorphisms. If we list the elements of D8, we have 4 rotations and 4 reflections. Because R to the 4 is the identity, R cubed is equal to R inverse, and our center has the identity and R squared in it. That means we have 4 inner automorphisms, and we can represent them by the identity, C sub R, C sub C, and C sub CR. Now, if we list where each of these send R and C, we note R goes to R or R inverse, which is R cubed. Those are the only 2 options anyway. And we see that if we take reflections that fix 2 opposing vertices, they go to reflections that fix 2 opposing vertices. So we have either R squared or R0. Now, if we consider orders of these inner automorphisms, each has order 1 or 2. So that's clear for C sub C and C sub CR, since C and CR are reflections. For C sub R, if I square that, we get C sub R squared. R squared's in the center, so we get the identity. That means in of D8 is isomorphic to Z2 cross Z2. So that's the group of order 4, which has every element of order 1 or 2. Now, for out of D8, that's given by this quotient group. Out D8 has 8 elements, in D8 has 4 elements, so this has 2 elements, so it's isomorphic to Z mod 2. Now, if we want to list all the other automorphisms, we have C sub R to the 1/2. We have this element's cube. Both of those have order 4. Since those are the only 2 elements of order 4, they're inverse to one another. Then we have C to the R to the 1/2, C sub C, and C sub R to the 1/2 cubed C sub C. We note here, R goes to either R or R inverse. Okay, that's coincidence because we're using n equals 4. Main thing is we're sending reflections that fix 2 opposing vertices to reflections that fix 2 opposing edges. So we have this interchange. Now, we have that the automorphism group of D8 is isomorphic to D8. So to see that, we just need to check the identity. Okay, we have an element of order 4. I'm going to conjugate by an element of order 2, and we see that we get element of order 4 inverse. So that means we have the generators and relations for D sub 8. As a final note, we could realize aught of D sub 2n as a matrix group. First, we have the group of affine motions of Z mod n. So these are going to be the bijections from Z mod n to itself in the form x goes to ax plus b, where a is in Z mod n star, b is in Z mod n. To each of these maps, I can assign a matrix. This will be 2 by 2. We have AB01. This will be a homomorphism if we carry composition over to matrix multiplication. Now, to bring automorphisms of D sub 2n into the picture, if I have the automorphism that carries R to R to the K, C to C times R to the L, I'll send that to the matrix KL01. This is going to be a homomorphism and a bijection, so I'll have an isomorphism. And it's a good exercise to go back and work everything out just using these 2 by 2 matrices.